Hello everyone. So we have two labs remaining today. That is experiment 6 and experiment 10. So I hope I'm audible. If I'm not audible, let me know. Um, All right. So we'll start with experiment 10 since our experiment 6 is a little longer. It needs a little bit more time to train. So we'll start with experiment number 10. I'm going to share my screen now. Just give me a minute. Wait. This is our experiment 10. So it is the same IMDb reviews. So we're going to categorize whether that review on IMDb is positive or negative based on the context. So we are going to use RNN, means recurrent neural network, in this problem. So let me just give you a brief overview of what RNN is. So let's say that you are reading a book. Okay, you read one word, then one sentence, then two sentences, three sentences. And while you're doing that, don't just remember a particular word or a sentence that you're reading. You're remembering the context of the previous sentences, and that is how you are able to understand the whole paragraph or the book, the whole context of the book, or the whole story. You're able to understand only then when we are able to, uh, you know, understand the context of the previous sentences. Context means the important part, right? The important part that is needed. We are understanding that, and we are basically building on that, and we are moving to the next sentence, and then we are continuing our story and making our understanding. That is how we are going to read a book. That is how we read books, right? So the same way we have designed our recurrent neural networks. This is how it works. It reads one sentence or one word, understand the context of that word, and move on to the next. And then it actually builds up its understanding, which can you can refer to it as internal state. Okay, we will get into that. That is actually the you know what we call as LSTM, long short term memory. So let's do first things first. We're going to import the necessary modules. I'm going to set the vocabulary size and the maximum sequence length. So vocabulary size means there are 10,000 vocabulary, means unique words available, and that will be considered for training that RNN. So we're not taking 100,000, so we have to take a vocab size. So these are the vocab size. In that, when your word matches to that vocab, that is no vocab size, then only that will be considered. And when you're saying maximum length, 200, that means every review will be converted to the length of 200. If it, let's say someone has written a review of 350 words, so it will take 200 words of it, first 200 words, and it will discard the next 150. So let's say someone has written only 80 words of 80 words of review. So the rest of it will be filled with, the rest of the review will be filled with, the 120 spaces will be filled with spaces actually. Okay, empty spaces. Run. And here we are loading the IMDb data set in XTrading. We are taking num words equal to web size. That is all. Here we are padding the sequence. Padding the sequence means the same thing which I explained in last class. Uh, so what we do is we are going to convert it the 60, let's say 70 word review to the 200 word review, and the 350 word review to the 200 word review. So that is what we are going to do in this. So basically, what the purpose we are actually writing this max length of 200 is the same. We are going to pad the sequence. That means we are going to make all the reviews which in the to the equivalence. Okay. So if it is 80, we are adding once again, if we are 80 words, when we are adding 120 empty spaces. If it is 350 words, we are removing the last 150 words and we are taking the first 100 words. Yes, Pawan, you have a doubt.
So the video not proper, sir, unable to see clearly.
Can you write your doubt in the chat box? Actually, you're not audible properly.
Okay, sir, video is not properly, sir. Now it came, sir, now it's came.
Yeah, Pawan, can you write your doubt in the chat box? Okay. Okay, video not getting clarity. So I'm going to turn off my video and will share my screen. Let's see. Yeah, it is actually due to bandwidth issues. So is it clear now? Pawan, is it clear now? Yes, please reply so that I can proceed. Okay, I'm not getting any responses from you, so I'm just going to assume that you are able to listen to me and you're able to see my screen. Okay, if I'm properly on. So, am I audible properly? Okay. So far we have discussed, we have imported necessary libraries, and in that we have imported pad sequences, sequential, embedding, LSTM, dense. So embedding and dense we are familiar with, right? So one thing new we have introduced is that LSTM. Okay. So, all right. So after that, we are going to take a vocabulary size of 10,000, maximum length of 200. And here we are going to load the IMDb data. Here we are padding sequences with the purpose that if I have a shorter review, I will make add some empty spaces and make it a review of 200 words. If I have a longer review than longer than 200, I'm going to just take the first 200 words. Okay, that is how I'm padding sequences. Okay, here I am making my model architecture. So everyone knows that model is equal to sequential. When I'm using model equal to sequential, then what I'm doing is I'm basically, you know, setting up a platform to make my neural network. Then I'm going to add new layers. So in this model dot add embedding input dimension vocab size and output dimension 32. Okay. So here what I'm going to do, I'm going to convert all those words into dimension of 32, 32 dimension vectors. So what embedding actually does, okay, what is actually done doing is it converts our words into multi-dimensional vectors, okay, and they become dense representations that capture semantic relationship between words based on their context in the training data. Okay, so we are getting our dense vectors, and that is capturing the semantic relationship between words and based whatever the data is. Okay, and whatever output that we are getting means the output that is dense vectors that we are getting, we are feeding it to the LSTM layer. Okay, now what is this LSTM actually? So let me give you an example. I've actually written this. Okay. So let's say we have a cat named Whiskers. Okay. So we are actually reading a story. Sorry. So we are adding actually reading a story about a cat named Whiskers. Okay. So LSTM units remember important details like the fact that Whiskers is a cat. Okay. Now, as I said, that it like we read a book, right? We read a book, and what we do is we gather our subconscious mind or whatever you can say, whatever our attention span is. We gather only important information for each sentence. We don't, you might have noticed that you don't remember each and every word of every sentence. You just get an inference from it. Okay, so means the important information that you need to understand the context. That's what we do. The same way, our LSTM does what? When we are talking about the internal state about the LSTM, it takes one input, it extracts important information and forgets the unimportant information, and it updates its internal state. Internal state means whatever the understanding it is. So you compare it to yourself, whatever understanding you have developed after reading 10 sentences. That is what it's and the LSTM internal state is. Okay. So if there are more LSTM units, it's like having more little memory cells in your brain, each focusing on different aspects of the story. So let's say you have units, 64 units. So 64 of these memories are working together to understand the story and make predictions about what comes next. So more complex data that we have, more units we should have. Okay, but if we are having too many units, there might be a chance of overfitting. So we avoid that and we keep that to the to the context that we need. So in simpler terms, we can say that more LSTM units you have, the more model can remember and understand the context of the data. Okay, so here we are having 64 units. That means 64 at the time, at one time, 64 of these memory cells work in parallel, allowing the model to capture more complex pattern and dependencies. So you just treat it as as your brain cells. The more brain cells you have active, let's say we say that often that our brain doesn't work at 100%. It works at like 2% or 3%. So some of our neurons are active and most of it is inactive. So let's say we have a particular 100 neurons active at one time, just a vague example. Okay, so we have a better understanding, we have a particular understanding, okay, understanding level. Let's say we have 1,000 neurons, no brain neural cells active at one time, then we will have a better understanding of things, right? The LSTM works the same way. Okay, so only difference is that LSTM at one point of time, it is going to work on a particular data set and it is going to understand only that data set, irrespective of our brain, processing two different data sets. Okay, that is why we need to keep it low, the neurons low, because we are working on a particular data set. And if we keep too many units, then it might overfit and it might be fixated on that data set itself. So then after we are using this dense layer and activation function as sigmoid. Okay. Now this what this activation function does, it gives one output and has a probability. So whenever we are actually working with a binary output, that means on that so it is a little bit different from categorical output. That means more than two categories. When we are using more than two categories, then we use softmax function. Okay, softmax function then we use, and we actually predict what is the probability of a particular category to be true. Okay, but in this we need only one probability because we are dealing with a binary data, right? That is why we need only one output. So if it is closer to one, then it is can be said as positive. If it is closer to zero, then it can be said as negative. Whatever doubts if you may have, you can write in a chat box. All right. So here, what I'm doing is I'm going to write the model summary. So here you can see there is an embedding layer and of 32 dimensions. There are 3,20,000 parameters because we know that we had 10,000 vocabularies, right? 10,000 unique words. So here is our NLSTM layer. So it takes all those and it takes and it creates the output that is a has that as a parameter. Now this is our density. So mathematically, what unit do is LSTM units process the word vectors by applying a series of matrix multiplication and activation function to update their internal states. So as I said, internal state is basically you can compare it with your understanding. Okay. And produce output that captures sequential dependencies on the input data. Sequential dependencies means the same thing, the context of the statement. Okay. That is what the whole story is about LSTM. Okay. So let's go to this, LS. So here you can see that we have an activation function as tan h. We call, if we are talking about the activation, what activation function do we have in LSTM? So that is status, and that is responsible for actually the whole operation. All right. We are talking about the final output, what LSTM layer is producing. So you can say, let's say the SSTM layer process the sentence, the cat sat on the mat by sequentially processing each word's embedding vector, right? And updating its internal state and generating an output representation of entire sequence. So it will just generate an output sequence. So let's go to this. So we have a little bit of more understanding. What will be the final output? So let me get, let me explain to it you the easier way. So LSTM is based on time steps. So whatever the final understanding that it will do, because every time I'm updating my understanding. So if configured to return only the output of last time step, the final output represents the processed information from entire sequence. So in last time step, we are getting the whole thing, because that is how we are updating our internal state. If configured to return the output at each time step, output at each time step provides information about the sequence process, whatever the sequence it has done. So basically, to return internal states, STM also provides information about the internal memory and state. So that is a different thing. Okay, the whole thing is to develop our understanding. Okay, so more it reads, more the output. Of course, it depends on this units, but also it depends on the size of the data. Okay, so more it learns, more it understands. That is what it is saying. So here we are going to compile. So here I'm going to write the epochs 2. The reason behind is that it is going to take almost a minute. Okay. So first of all, I'm compiling the model with binary cross entropy. We know that why we are not using categorical cross entropy, because we have only two. Uh, and, you know, we have only two possibilities. If we have more than two possibilities, then we will use categorical cross entropy. Optimizer is Adam, and I've already explained what this optimizers and accuracy. Comparing that with your three gem trainers. One actually tells you about what mistake you are doing. One corrects you, and one just checks your accuracy. Okay, here I'm going to train our model. So we are starting to train this model. So you can see that every batch it learns, it is understanding its, I mean, in this updating its understanding, and the you know, accuracy is increasing. We'll just take 1 minute more. So basically, it takes a little bit of time to train the model uh, based on our GPU and our data sets. Basically, it is whatever processing power we have in our hardware. So you might be required to actually run 10 epochs. So that will take around 12 to 13 minutes. Okay. Are there any doubts? We are training this. You can write in, the group chat. If there are any doubts. Now, in two epochs itself, I'm getting accuracy of 86%. That's So whenever there is a situation that model.fit is failing and not understanding, okay, why it is failing, everything else is working properly and all things are correct, you can just restart the session and run it all. So we have an option here to restart session and run. It's happened to me right now. One of the blocks might not be working as desired. Now we are evaluating the model. So you can see the value loss is being decreased. Loss means decrease means increase in accuracy. That means we are less less far away from the truth. Means the accurate decisions. Now you can see that I am getting an 86.5% accuracy in two epochs itself. Okay, you might be running for 10 epochs or maybe 20 if that depends on you. Okay, so now we have this. So this concludes our experiment, and that is recurrent neural network. Now we go back to CNN. Okay, that is our image dogs and cats classification. Okay, so that this is our experiment 6. So you know what I'm going to do? I'm going to run all of this because this is going to take time. Because this experiment is going to take time to train. I'm going to first make this epoch because one epoch of it will take at least 10 minutes if not more to train. So what I'm going to do first, I'm writing is it as epochs 1. Okay, and then I'm going to execute every block of code. So while I'm going to explain to you, this is going to train, so we can save time in that. First, let's just see what this is. So it is we are actually connecting our Google Colab to the Google Drive because we have to take the files from there. How we'll do that? We write this from Google Colab, Google.colab import drive and drive.moon content drive. You can also just go to the files and you can just click on here and you will see this code appearing. Okay, let me just sign in and so it will be like this. So let it get into this first step by step, and then I will tell you how we are actually getting the images. Okay. So the problem statement is that we are going to get some images, around 500 that I have, not that much I have, which is required. Okay. First of all, so this problem is about we are going to get number of images, and we are going to train our model based on those images. Okay, so that is what CNN is. As RNN is used to understand textual data, our CNN is used for understanding images. Okay, so here is our root path. So I will explain that. And this we don't actually need. Here we are actually training. So we will train for one epoch only. Let it train. Uh, Meanwhile, let's get into how actually we are going to build this project. So the first thing that you will do is create a new folder named cat.project here. Okay, because that is how your code is designed. You want to, name your project something else. The same you have to do, same editing you have to do in your projects. Okay, want to take those things so that whatever folder you name there, like here I'm taking root path cat doc project. If you name it something else, then you have to, you name it something else, then you have to change this also. So right now I don't want to change. That is why I'm naming my project as cat doc project. Okay. So when I've created this folder, I will go inside this folder and I will create one more folder that is pet images. Okay. So don't worry about these things first. Just focus on this. So pet images I will create, and then I will create more two folders, that is validation and train. Okay, more two folders, validation and train. So in now in both now mind this, in both these validation and train folders, right? In both these validation and train folders, I'm going to create two more folders as cat and dog. Okay. Don't worry about that. We have already have this. We don't already have this. So I have this because I've uploaded it. Okay. But what you will do, you will just create two empty folders of name cat and dog in both validation and train folders. Okay. So now what I'm going to do, I'm going to just go to Kaggle, dog images. Okay. I'm going to, take this data and I'm going to download all. Okay. When I download all here or somewhere else, I will get something like this archive. Okay. When I open this, I'll get all these files, dog and cat PNG and everything. Okay. So finally, you will get two folders named dog and cat. Do one thing, copy those folders in a new folder in your on your desktop screen. Okay, like this. Make a separate folder of that and zip those folder and make them a file. Okay, zip folders, zip dog and cat folders and make them files, zip files. Okay, next step that you will do, you will upload those these zip files in your Google Drive. Where in your Google Drive? Here. Okay. Here in your Google Drive, you're going to upload these zip files. So why am I doing this? All this trouble, why am I taking? The reason is I don't have the divided data. I have to divide my data in training set and validation set. Means training set and testing set. I don't have that. I have all the data here itself. And this is the first, this is the step that we are going to take after making all the folders. Okay. Now I'm not supposed to do it manually. So rather, what I would do is I would, so I'm not going to run this. Okay. I run this, then all these files will be again copied in my data, in my data. So I'm just going to explain to you how this is going to work. So first you're going to so what I'm going and doing here is I'm writing a code so that you are able to split your data and you are able to distribute that data in equally in those training sets, in this validation and train, and these folders cat and dog. Okay, so let's say I have 500 images of cat and a 500 images of dog. So when I'm going to this train data, this cat folder must contain 400 images. This dog folder must contain 400 dog images, and this validation folder, this cat and dog folders should actually contain no 100 images of cat and dog each. Okay. That is what my target is. Okay. So yeah, splitting image. So first of all, what I'm going to do is, since you don't have that in, your lab, so I'm going to download this and I'm going to upload this here itself. You can download it from your chat box, or if you go through this video, then you will see, okay, what are the steps that I'm going to take. Okay. So so these are these libraries that I'm going to import. And then I'm writing the function to extract zip files. So we have zip files, right? We have to extract information from that. Okay. And then I'm writing function to move files. You will see what actually we are actually doing. Okay. And this is for counting the files. So right now what I have, dog zip path. Okay, dog zip path. Now this is our zip file. Content, drive, my drive, cat dog project, pet images, and dog. This is where our zip file is there, right? I'm just copying the path. I'm just writing the whatever path my zip file is on. Okay, and the same for cat. And this is our target directory. In pet images only, I want to in this subfolders of that pet images, I want to copy this the data. Okay. What I'm going to do, I'm going to copy all this in a temporary directories. Extracting the zip files to temporary directories. First, I'm going to write this dog extract directory content dog temp, this, and then I'm going to make a directory here. Okay, if it is already there, then it will not show me error because I'm saying that exist okay is equal to true. Okay, now I'm calling this function extract zip. We have already defined this. Okay, so what are the parameters? The zip path and the extract directory. So whatever zip file I have, the zip path I have, so that I can get the contents of the zip file, and the extract directory means the destination folder. Okay, zip path extract to. So extract to parameter is means the destination directory. Okay, so here I am reading that zip file and I'm extracting everything and I'm copying that into extract to means this dog extract directory. Same I'm doing with cat. Okay. Now I'm going to print this. So don't worry about printing. So if not, so let's say if there is nothing inside dog extraction directory, if there is error. So this I'm doing just to prevent error so that I can understand, okay, this is the error. So if it is empty, then it will show me this, okay, this dog extraction directory is empty. So if the extraction is successful, then I'm going to proceed further. I'm taking that dog directory name as dog, and then I'm taking its path. Okay, I'm joining that. This is a predefined method, dot join and everything. Same I'm doing for cat. Now I am introducing our split ratio. Okay, split ratio is 80% and 20%, 80% for training and 20% for validation. Now when I'm doing that, that means 80% of the data, 80% of the images should be copied in train folder, right? This train folder and where it is. Yeah, and 20% of the data should be copied in validation folder. That means let's say I have like 1,000 images, right? So 800 should be copied inside this uh, train folder and 200 should be copied inside our validation folder. And subsequently, it will be divided into cat and dog folders itself. Okay, that is what it is doing. So right now I'm taking this dog files and cat files, listing directly as subdirectory, whatever we have got. And then we're going to shuffle it. Why we're going to shuffle it? Because I don't want to make a sequence every time when I do this. I don't want to make a pattern. Every time I'm going to shuffle all those images. Okay, means random data and unbiased data is being distributed. So here we are getting the split index. I'm doing nothing but multiplying this, uh, the length of dog files that is, let's say 500 into split ratio. So 400. Okay. So you know that we have a list, and if I use this dash, colon 400 by indexing, so I will get the first 400 images. Okay. 400 after means I will get from 400 to the last. Okay. So here is just going to do nothing. It's just going to print this, whatever the index is. Okay. Now here I'm going to create the directories. I'm going to create train dog and cat, train dog and dog train cat validation. Okay. So if it is okay, then it is not going to show any error. Now, when I've created those directories, what I'm going to do, I'm going to move files. So this move files. I have defined this function, move files. I'm doing in this files, source directory and destination directory. For file in files, every one of them, I'm using this shuttle, whatever I've imported this dot shuttle dot move to move this file from source directory to the destination directory. Okay. So you can also write this print move file so that okay you can understand that whether this which file has been moved on, which is okay. So I'm doing this for dogs. I'm moving this. When I'm writing this dog split index, that means I'm writing. Let's say it is 400, so I'm writing 400. That means what? It will take first 400 data. Okay, in the list, it will just take first 400 elements. And here I'm writing 400 colon. That means whatever after 400, okay, whatever after 400 means after the index 399, 0 to index 399 will not be considered. And after that 400 will be considered till the end. Okay, that is what it is going to be. Okay, so that is how we are dividing it and we are copying in our train folder and validation folder. Same thing we are going to do with cats. Okay, now our uh, whole thing is done. Our files are moved. Everything is here. I'm just going to print this so that I can have an understanding. Now, while you are running it, make sure your folder names are same. Okay. So here we are actually able to train this. We're getting the value accuracy of 90/50. It's a pretty good, accuracy in one epoch itself. So you can run 10 epochs and it will take almost 1 hour, 30 minutes to 2 hours of time. Okay. Save time we have done. This only one epoch. So now that we have splitted our images, what I will get in every validation data, you will see validation data in every folder, you will see, images. Okay. Till you don't see that, that means it is not complete. Okay. So better to check. Have that already. Okay. So now, since we have those, let's get into this. So here we are importing all those libraries that I need. And let's see this. We are importing VGG16. So do you remember in experiment, which experiment we are actually did? I think experiment 9, experiment 7. We use this pre-trained convolution neural network VGC16. It has 16 layers and it is pre-trained, so we don't need to train it. Okay, so we are importing that for our, to generate a better algorithm. And we'll see why we are using this image generator and everything. We see you already know. Okay. So here again, you can see that I'm actually trying to connect to the Google Drive. Okay, and here is our root path. So the root path that is given in your lab is this. Let me see. Yeah. Yeah. So read root path that you are getting in your project, whatever lab it is this cat dog project 203, this and all this. So, it's better to remove this because it is supposing that it has one more folder inside that it has this called cat dog project. I am just copying that cat dog project inside the home page of my drive. So you need to remove this if you are, doing the same thing as I'm doing. So you need to remove this and you have to write the path like this. Just one folder I'm removing. Okay, directly cat dog project. Okay, then I'm going to import that OS and I'm just getting this. Okay, uh, this is our drive. This is our folder. Imagery size. All we want all the images to be 224 into 24. This is our train and valid path because that is how I have done this, right. In this folder, we have this cat dog project. Inside that cat dog project, we have this pet images. Inside that, we have validation and train. Now we do not have nothing to do with train, cat zip and dog zip. The purpose of this is over. You can even delete it if you want. Okay. So here what we are doing is we're importing our VG16 library and we are downloading the data with that. Now, and when I'm writing weights is equal to image net, that means what? We are actually telling the program, let's use all the knowledge that you actually being trained on. So ImageNet is actually the data set, the huge database of images that this program, this VGG16, VGG16 is being trained on. Okay, it has been trained on ImageNet. So I'm just writing weights is equal to ImageNet so that when uh, I train this, sorry, when I use this, it uses all its knowledge that is in. So when I'm saying, okay, this image size and this is 3, so you must have heard that when you are actually deciding a color, you get 3 dimensions, 0, 0, 0. Okay, so if it is 0, 0, 0, that means it is either black or it is white. Okay, and most probably I think it's black. Okay, so as you use this RGB, RGB 0, 0, 0, it is black. Okay, so white is 255, 255, 255. So now red is 255, 0, 0. So these are the 3 dimensions that actually, decide the shade of the color that we are actually using. Okay. And include top false means what? Final layer we are not going to take. Okay. Not we are not going to take the classification. We're just going to take the learning. Okay. Now I'm just going to print the VG16 layers. Okay. So what layers are those? This has the input layer. As I said that there are convolution layers and there are max pooling layers. You can see these layers. Okay. This is our VG16, VGG16. These are the layers that are being used to build this network. Okay. Now, what does that mean that I don't want to train existing weights? Means I have this VG16, VGG16 layers, and I do not want it to, train more. So that is why I'm writing. It has already been trained. So that is why I'm writing layer dot trainable is equal to false. When I'm writing this, in the next step, what I'm doing is I'm checking whether it is trainable or not. So it is saying, okay, all those are not trainable. None of this will be trainable. Whether not convolution layers, not pool layers. Here I'm writing summary of it. So what it is, input layer, which is going to take this 224 by 224, image with 3 dimensions of color. And then what is going to do? it is going to pass through this convolution layer. Okay, it is going to pass through this convolution layer and is going to zoom in through 64. Let's say there are 64 detectives and they are working on a same case, and different aspects of the case they will investigate, and it will they will produce an output. So that is what we are doing. We are using 64 binoculars, let's say, to focus on the data and take the important part. Okay, so we are using two convolution layers, and then we are using one max pooling layer. So what this max pooling layer is doing, it is doing dimensionality reduction. So it is taking the important part and it is rejecting whatever the unnecessary part is. That is what it does in CNN network. That's what in the last class I explained. Okay, again it is working with 112, 112. Okay, convolution layer, and it is digging in deep. Again, it is with one more pool layer, it is reducing its dimensionality. So on and on, we are going to dig deep into the image, and we are going to develop our understanding. Okay, this is no just checking how many folders it. So this is where we are actually going what? We are actually building our network, our sorry, our architecture, our neural network architecture. So first is sequential layer, that means platform for networks. Then we add this VG16 layer. So whatever output VG16 layer is going to produce, we are going to flatten it. So it's a 3D output. We are going to flatten it into the array of 1D. So now model dot add dense. Again, we are introducing a dense layer with a and with an activation function of this ReLU, so that we can introduce non-linearity in that data. And finally, we are using this activation function as softmax. So again, we have this categorical. So whether it is dog or it's a cat, so we are using softmax, so it would produce, okay, what probability of it is a dog, what probability of it is a cat. Okay, so that is how you will decide whether it is a dog or a cat. Okay, so model dot summary. So you can see this. This is the output shape that it is going to use. This is the 512 output shape that is going to be flattened layer is going to produce 25,088, because now it is producing an array of 1D vectors. Now we're going to use this dense, and that's it, the dense layer, and that is what it's going to do. Now the final dense layer, because of that softmax function, is to output. Okay. Any confusion so far? So, anything you want to ask, you can write in the chat box. If your audio is working properly, you can just speak. Considering that you have understood, let's proceed further. So that's not much is remaining. So here we are compiling our model as we used to. Here we are using image data generator. Okay. Let's come here and see what our image generator data generator does. So let's say there are two pictures in which the lighting is different. The lightning is different, the shade is different, but they are two same pictures. So how will that be understood with the computer? So that is where image data generator comes in. Okay, so it does nothing. It does nothing, but it's like a smart assistant for a computer. It helps your computer show a lot of pictures in different ways, so it gets better at recognizing things. Even they are a bit different. So bit difference means the same thing. That if there is a uh, let's say you are using filters in your Instagram, so there are different type of filters like New York or something like. There are many. Okay, I don't actually have understanding of all the filters, but in your Instagram filters, so there are many shades of in which you can actually present your profile picture. So but the profile picture is same. So here, based on that data, how you will compare the both those switches, you will use image data generator to actually uh, perform that operation. So when I'm using that, that means I'm training my computer to understand that, okay, if there is a deflection, if there is a shear range, handle it. Okay, I'm rescaling my image and then handle. Now I'm based on that, whatever data gen I have, trained data gen or generation and test data gen I have actually got from the image data generator. Now this image data generator is getting me those corrected images, irrespective of those shadings. Let's say, yeah. So there is a little bit of difference. If there is a little bit of difference, let's say same lighting condition or different lighting conditions, all those are being you know handled using this rescale and image data generator. Okay. After that, when we are getting that the final output from image data generator, we have images irrespective of our lighting effects and everything. Okay, so that is why we are getting okay. Now I am saying this training set is equal to this pet images dot train this category. Now it is saying that I have found 800 images belonging to two classes. That means dog and cat. Same for test data set, 200 images belonging to two classes. So if you remember that we used our split ratio as 0.8. That is why it is doing this. Now here I'm fitting the model. Okay. This took around 10 minutes, more than 10 minutes, 11 minutes actually. Okay, 11 minutes, 20 seconds. So after this, we have done this. Let's plot this. Again, loss and not being properly. We are not able to do this because it has taken a little bit of time to actually. So if I run this again, then it might plot, but that will take a lot of time. So this is just a plotting. So you can uh, this is just plotting. You can actually do, then you will get a result. Here we are saving our whatever model we have. We are saving it in this model.vgg 16.5. You see this in my drive. In the here we have this model VGG 16.h5 that I saved. Okay, now we have 10:38 a.m. today. Okay, now we have saved our model. We are actually in the process of doing that. So it will take a little bit of time. But due to time constraint, I'm not able to show you the perfect, figure that I was supposed to. So meanwhile, it is, actually saving. And if you have any questions, you can write it on the chat box. It is going to take like 2 minutes in that. Sorry, to save that. Whatever you saw here, we had three epochs. Actually, I was running three epochs that ran for 30 minutes, and I was actually plotting, recording the that. It was proceeding, so it might not be doing that for one epoch. Okay, this is our vibrate. It doesn't have any, doesn't have any content as cat GPT. So what I'm going to do, let's proceed. So it is taking one more image and it is actually going to process that. Okay. I've uploaded one more cat image. Okay. This PLT dot image I am read is going to read the contents of this cat dot JPG and it is going to plot this when I'm showing this PLT dot IM show it is going to print this. So let's say if I want to like there's a little different vector that you got. Here is the prediction that you are going to do whether it is a cat or it's a. So this concludes our lab 6, which was CNN to actually understand the images, classify them based on the probability. Our model is trained enough to understand a particular new image and understand whether it is a cat or it is a. So, are there any questions? There are no questions. Guys, thank you very much. I believe there are no questions. If there are any questions, um, you can ask in chat. So I'm just uploading that splitting images once more. So download that, use that to divide your file, extract and divide your file. Okay, this is your IPINB file. And you can do that. And if you, in case you want this, I'm just going to give you this too. So we can actually, if you have downloaded this, download this, and then you can end the call. If you want all those lab files, then you can actually contact me for that through your seniors. Sorry, through your faculty. I will let you know. I will just send you all those files that you have been actually taught. Okay, so let's end this call. Thank you very much. That will conclude all 10 labs.